Okay, in the following two examples, we are given two definite integrals. And what exactly is a definite integral? It's an integral that has an upper limit and a lower limit of integration. And so what we're talking about here is we're looking at a function specifically over a set of values. And the instructions here say use areas to evaluate the integral. So what I've done here, I've provided a graph. We're going to graph these and we're going to take a look at it and we're going to see, well, what in the world does the graph look like and how in the world can I compute an area from it? So the first one is relatively easy. What we're going to do is we're going to take a look at it and we see that it's a linear function. So let's go ahead and draw this line. Well, it's a line with a y-intercept of 10 and it's got a slope of 2. So let's suppose that right here is my intercept 10. All right, so I'm going to do a rise over run there. And let's just pretend that this is what it looks like. Okay. And I'm going to tell you that this right here is -5. And let's pick some number, oh, I don't know, maybe about right there. We'll call that +5, and actually maybe that's too far out. 1 second. Bring the graph back in place. Okay. Let's say right about here, just so it's symmetric. There we go. All right, and let's bring this up here. And so what we do need to know are the y values. So right here, the y value down here at the bottom is 0. All right, y value there is 0. And then the y value here, all right, it's not drawn to scale, but the y value there is 20. So what you need to see here is that we've got this shape here. It's a triangle, a right triangle. And so what I'm going to do is I'm going to take this integral problem and I'm just going to turn it into the area of a triangle. And so let's see here for a second. If I am looking at, suppose the height of the triangle, all right, the height here is 20 units. And now if I'm looking at the base of the triangle, the base here from -5 to 5 is 10 units. Okay, so to find, you should recall the area of a triangle. The area of a triangle is 1/2 of the base times the height, or base times height divided by 2. So that's relatively easy now to figure out. I'm going to have 10, the base, times the height, which is 20, divided by 2. So this gives me 200 divided by 2, which is 100. So what is the area under the curve from -5 to 5 of the function 2x plus 10? Well, it's 100 square units. Okay, so our answer here being 100. All right, and there's really nothing to it. Okay, so we're using just geometry to find an integral, and that's what you need to understand, is that this is the area under the curve. All right, let's take a look at the second question here. And on this one, maybe you don't quite know the shape of the graph, but let me show you something that you might know from maybe a college algebra or a pre-calculus course. That is that you, at that point, had a function that looked like this: x squared plus y squared equals 16. So you might notice that this right here is the equation of a circle with a radius of 4 units. Okay, what they're giving us here when they want us to examine this function, square root of 16 minus x squared from -4 to 4, is a semicircle. Let me show you what I mean. What we do is we will solve for y. So we're going to first say y squared equals 16 minus x squared. And then we're going to say, okay, let's take then the square root. So y will equal plus and minus the square root of 16 minus x squared. So we're going to be examining then a semicircle. All right, so let's say that the radius here is 4 units, because we knew that from way back over here that the radius was 4 units. So I'm going to mark off, let's say 4 units, -4 this way, and about equidistant 4 units this way. And then of course you can come up here and and say that this is also 4 units. And then you draw your semicircle. And I'm not an artist, I don't claim to be one. All right, so pretend that's a semicircle. All right, we look at this right here. This radius here is 4 units. So how would we find the area under the curve of a semicircle? All right, so it's a semicircle. Well, we know that for a circle, the formula for area is pi r squared, right? So for a semicircle, it would have to be half of that. So we really don't need to know any kind of advanced integration rules here. We're just using geometry, properties of geometry, formulas from geometry. Pi r squared divided by 2. Our radius again is 4 units, so pi times 4 squared divided by 2 gives me 16 pi divided by 2, which is 8 pi. So my area here under the curve, square root of 16 minus x squared from -4 to 4 is 8 pi, and we might say square units because we are talking about area. But other than that, it's nothing really to worry about. We're using some geometry. We can use our own intuition in graphing and calculate the area under the curve. And so we get the area, again, under this semicircle. And I'm shading it in so that you see this is what we've calculated. The value of that area that I'm shading yellow here is 8 pi. So, as always, I hope this video was helpful, and if it was, remember, like and subscribe.